Welcome back. We are in our discussion about atomic basics. And what do we mean by the atomic basics? Well, start off with our atom here, right? And we say that the atom is composed of some particles. And although there are a bunch, or several, let's put it that way, the three we want to focus on are the electron, the neutron, and the proton, correct? And the electron, we said, has an assumed charge of -1. The neutron is neutral with 0, and a proton is +1. They have masses of 5.486 times 10 to the -4th AMU, 1.0087 AMU, and 1.0073 AMU, correct? And we said that these two guys are found where? In the nucleus. And that where's my electron found? Well, really, anywhere outside the nucleus. And there are places where it's most likely to be found, and we will talk about those next chapter. But that gets very complicated, so we don't want to get into that just yet. And then we talked a little bit about how do we represent, what kind of representations do we have for atoms? And I talked about two. I said I can have something like an O18. And what does the O stand for? Well, that is my symbol for the element, right? And what's the 18 stand for? This is what we call our mass number. And what's the mass number? It's equal to the number of protons plus the number of neutrons. Good. Now, if I know the symbol right here, it means I can also figure out the number of protons, right? Because it is the number of protons which defines the element. If I have oxygen, that's oxygen, and I looked up on the periodic table, I would see that there's an O and an 8, and that 8 means what? That is the atomic number, right? The atomic number, and that is the number of protons. So if I look up here, if I look here, I can see my symbol is oxygen. I know that there are 8 protons. If I have 8 protons, then I can figure out from the mass number the number of neutrons. So in this case, there would be 10 neutrons because I have 18, a mass number of 18. That means the total of protons plus neutrons is 18. So that's one way we can look at the symbol and figure some things out. There's another symbol that we can use, which is something along the way, along the lines of uranium 92 238, right? Once again, my U stands for what? That's my symbol, right? Uranium. Uranium, right? What's my 238? My 238 is my mass number. And what's my 92? My 92 is my atomic number, right? The number of protons. Good. Now, sometimes, I use a different color here too. Sometimes we see some positives or negatives up here. And what does that mean? That means I have a charge on the atom. That means that the number of electrons and protons are not the same. So what is my charge? My charge is really what? The number of protons minus the number of electrons is my charge. So if I have a positive charge, that means what? I have more protons than electrons. If I have a negative charge, I have more electrons than protons. Good. And so that's kind of where we started, and to give us an overview of the atom and the constituent parts of the atom and how we can kind of interpretate some symbols. Now let's move on. Consider an atom of iron 56. What is the mass of the particles in the nucleus? Okay, so we only want the mass of the particles in the nucleus. What particles are in the nucleus? We want to know what? The number of protons and the number of neutrons. Good. We have iron 56. When I look on the periodic table, I see that iron has an atomic number of 26. So that means it has 26 protons. If it has 26 protons and the mass number is 56, it must have 30 neutrons. Okay, so let's figure out the mass. I have 26 protons times what? 1.0073 AMU plus 30 neutrons times 1.0087 AMU. And when I use my calculator here, 26 times 1.0073 plus 30 times 1.0087, I get a 56.4508 AMU. Good. 56.4508 is AMU is the mass of the particles in the nucleus. Now let's read on. What does it say here? The actual mass, that means when they actually mass the nucleus, the actual mass is 55.92068. Huh? Wait a minute. Can that be right? How can the actual mass be 55.92 when we just calculated that the mass of the particles making up the nucleus is 56.45? I think we got a problem here, folks. What do you say? Well, let's first look at this difference. We have 56.4508 minus 55.92068. How much mass are we talking about here? Okay, minus 55.92068, and we get 0.5301 AMU. That's the difference between our actual mass and our calculated mass, and this is something we call mass defect. Okay, so what is mass defect? That is the difference between the sum of the neutrons, the sum of the mass, sorry, the sum of the mass of neutrons and protons forming the nucleus and its actual, its meaning, and the nucleus's actual mass. Got it? The difference between the sum of the mass of the particles forming the nucleus and the nucleus' actual mass. And this mass defect, this sum is always going to be greater than the actual mass. How can that be? What happens here? Well, here's what we have to understand is I've got some neutrons and some protons. We'll say that neutrons are going to be blue and my protons are red. So I have some neutrons and protons that are just hanging around outside in the universe. And you'll find that's not a very stable situation, that they prefer to actually be in a nucleus where they are packed together. Oops. Where they are packed together. Good, and that's a more stable situation. And what happens, what causes the stability in one part is energy is lost in this process. Energy is released when these individual neutrons and protons come together to form a nucleus. Good. And so where does that energy come from, I guess, is the question. So we have individual protons and neutrons. They come together to form a nucleus. Energy is released. Where does that energy come from? Well, we have to think back to our good old buddy, Albert Einstein, who said E equals mc squared, where the energy is equal to the mass times the speed of light squared. What does this really mean? He's saying that energy and mass are the same things, just different forms. So, where did the energy that was released come from? It came from mass. What mass? It came from the mass of these individual particles, which were converted into energy, some energy, and then released. Good. So that's kind of where our mass loss went. The mass was converted into energy. This energy was then released. on the formation of the nucleus. And that's what we call binding energy. Nuclear binding energy. And what is nuclear binding energy? Energy released. Simply stated, it's the energy released when a nucleus is formed from its neutrons and protons. Got it? And this energy comes from the mass parts of the neutrons and protons, and that's why we have the mass defect. Okay, so good. We've learned something about nuclear binding energy, and we've learned something about mass defect, right? Okay, good. Moving on. What's the next thing we want to learn? Consider copper with two naturally occurring isotopes. Hey, okay, isotopes, that's a new word. Isotope 1 has an abundance of 69.15% and a mass of 62.930. Isotope 2 has an abundance of 30.85% and a mass of 64.928 AMU. And we want to know the average atomic mass. Okay, so there are two big words here, or two sets of words we need to understand. We need to understand isotopes, and we need to understand average atomic mass. So, isotopes. Isotopes. Okay, remember, I said that what really makes an element? We said that an element is defined by the number of protons, right? If it has 6 protons, it must be carbon. But what if it has 6 neutrons? It's still carbon? Yes. What if it has 7 neutrons? Still carbon. What if it has 8 neutrons? Still carbon. As long as it has 6 protons, it's carbon. So we can have a situation, and we'll look at carbon, where you can have carbon 13, carbon 14, and carbon 12. In each case, I have 6 protons. But how many neutrons do I have? Well, 6 neutrons, 7 neutrons, 8 neutrons, correct? These are all carbon because they all have 6 protons, but the number of neutrons changes, and that's what we call an isotope or isotopes. That is a case where you have the same element, but different number of neutrons. Okay? And we call those isotope. Isope meaning same, right? Good. Isotope, same element but different number of neutrons. Now, we also learned something here, and this is related to isotopes, and this is my average atomic mass. Good. I'm going to abbreviate that AAM. And what is the average atomic mass? Well, when I look at my periodic table, I'll see carbon. Up here, I'll see a 6. And when I look at the bottom, at least on my periodic table, I see a number in red, and it is 12.0115. This is our average atomic mass. It is the number at the bottom of the periodic table. And what is that? It is the weighted average, not a normal average, a weighted average of all of the naturally occurring naturally occurring, how do I spell occur? Naturally occurring, of the naturally occurring isotopes of an element. Okay? It's the weighted average of all the naturally occurring isotopes of an element. And what is my actual equation for this? Average atomic mass is equal to the mass of isotope 1 times the abundance as a decimal, not a percentage, as a decimal. Abundance as a decimal of isotope 1 plus the mass of isotope 2 times the abundance of isotope 2, once again as a decimal, plus so forth. If I have 3 isotopes and I do this with all 3, if I have 4, and so forth. So that is the equation we want to use. And so let's take a look and see if we can do this. We want to figure out my average atomic mass. So I want to take my mass 1, here's my mass 1, 62.930 AMU times abundance 1, and I have to make this a decimal. So I move my decimal point. I want to use a different color here. Move my decimal point 2 places to the left. There we go. So that's going to be what? 0.6915 plus mass 2, 64.928 AMU times my abundance 2, and I want to convert that from a percentage to a decimal, so I move my decimal 2 places to the left, so I get 0.3085. Good. So to take up my calculator, I'm going to take 62.93 times 0.6915 plus 64.928 plus 0.3085, and I get a bad number. I got to do that again. 62.930 times 0.6915 plus 64.928 times 0.3085. There we go. I get 63.546, and I'm going to end up 0.64, I believe, in terms of sig figs. There we go. 63.5464. And what did I do? I took the mass 1 times abundance 1, mass 2 times abundance 2. So here you go. You're on your own. I'll give you some time. Why don't you go ahead and pause me, work on this. When you're done, unpause, and I'll give you the answer. Well, you come up with an answer? I hope so. Here's the way I would work it. I'm going to say abundance mass 1, 35.97 AMU times abundance 1 as a decimal. So I have to move my decimal point 2 places to the left. So I have 0.00337 plus mass 2, 37.96 AMU times abundance 2. Have to move this decimal 2 places to the left. 1, 2, and I have 0.000, those are zeros, 63 plus mass 3, 39.96 AMU times my abundance, move my decimal 2 to the left, 0.9960, and let's run some numbers here. So hope I have better luck with my calculator this time. 35.97 times 0.00337 plus 37.96 times 0.12363 plus 39.96 times 0.9960, and I get 39.94. Does that make sense? 39.945 AMU. I think we're not going to be able to get this many sig figs. I think the answer is 39.95 when I round that up. AMU. Good. And once again, sig figs here are not quite as important as in other places. They're always important, but they're just very difficult to see. And do your best with those. Okay? Does that make some sense to you all? I hope it does. That should just about do it for today. Okay? See you later.